Myself Likit Vedi, currently studying in Sri Venkateswara College of Engineering. I am pursuing in 3rd semester. Course name Computer Organization and Architecture. Today I am going to explain floating point representation and IEEE standards. Introduction to floating point representation. Floating point representation is the method used in computing to represent the real numbers. It allows for a wide range of values by using a format that includes significant, exponent, and sign. This representation is essential for scientific calculations, graphics, and engineering applications. Historical background: early computing, evolution of number system, necessity for standardization. Early computing period. Initial computing efforts utilized fixed point arithmetic, which lacked the flexibility needed for extensive scientific and engineering calculations. Evolution of number system. Progression from simple binary system to more complex floating point representations highlights the need for a standardized approach to enhance computational power. Standardization imperative. The diverse and inconsistent methods for floating point representation in early computing necessitated a unified standard to improve interoperability. Understanding floating point basics. Components of floating point numbers. Components of floating point numbers. Floating point number consists of three primary components: sign bit, exponent, and mantissa. Each play a crucial role in value representation. Sign, exponent, and mantissa explain. The sign bit determines the numbers positively or negatively. The exponent defines the magnitude, and the mantissa carries the significant digits and precision. Normalization process. The normalization ensures the floating point numbers are represented in their standard form typical by adjusting the exponent and mantissa to optimize precision. Components of floating point representation. A floating point number consists of three main components: a sign, exponent, and significant. The sign indicates whether the number is positive or negative, while exponent determines the scale of numbers. The significant represents the precision bits of number, capturing its significant digits. Normalized versus denormalized numbers. Normalized numbers have a significant, that is, scale to fall within a specific range, usually 1 or 2. Denormalized numbers allow representation of numbers closer to 0, providing gradual underflow. This distinction helps maintain precision and range for floating point arithmetic. Precision and range. Representation values, rounding methods, impact, and calculations. Representation values and their range. Floating point formats can represent a vast range of values, but precision is often limited, affecting calculations and results. Rounding methods in IEEE 754. IEEE 754 specifies several rounding methods, including round to nearest, round towards 0, and round towards infinity, affecting numerical operations. Impact of precision and calculation. The precision of floating point representation directly influences the accuracy of mathematical operations and algorithms. IEEE 754 Standard Overview. The IEEE 754 standard defines formats for representing floating point numbers in binary and decimal. It specifies how numbers are stored and how arithmetic operations are conducted and how rounding is managed. The standard aims to ensure consistency across different computing systems and platforms. IEEE 754 formats. The IEEE 754 standard includes several formats, the most common being single precision 32 bits and double precision 64 bits. Each format has defined numbers of bits for sign, exponent, and significant. The choice of format impacts the range and precision of representable values. Format details of IEEE 754. Bit layout, binary and decimal representation. Firstly, bit layout. The bit layout of IEEE 754 defines formats includes distinct sections for sign, exponent and mantissa, crucial for understanding the binary representation. Binary representation in IEEE 754 formats allows machines to process and interpret floating point numbers efficiently, using bits to define values precisely. Decimal representation and special values. Conversion of binary to decimal is essential for human readability. Also, special values such as NaN, not a number. NaN means an infinity, are defined within this framework. Rounding modes in IEEE 754. IEEE 754 specifies several rounding modes to handle cases where results cannot be represented exactly. The four primary rounding modes are round to nearest, round to zero, round towards positive infinity and round towards negative infinity. Correct rounding is crucial to minimize errors in floating calculations. Floating point representation errors. Floating point representation can introduce errors due to rounding and truncation. These errors can accumulate in iterative calculations, leading to significant inaccuracies. Understanding these errors is vital for developers to implement reliable numerical algorithms. Special values in IEEE 754. The IEEE 754 standard includes representation for special values such as infinity, NaN, not a number, and 0. Infinity represents overflow situations, while NaN, not a number, is used to denote undefined or representable values. These special values help manage exceptional conditions in floating point arithmetic. Applications of floating point representation: scientific computing, graphics processing, machine learning, financial system. Scientific computing. Floating point representation is a foundation in simulation, modeling and calculation that requires high precision and wide range of values in scientific research. Graphic processing. In graphics, rendering floating point numbers enable detailed representations of colors, textures and transformations for realistic visuals. Machine learning algorithms. Machine learning heavily relies in floating point arithmetic for processing largely datasheets and executing complex calculations effectively. Financial system. In financial system, the floating point is employed to ensure accurate computing in currency representations. Applications of floating point representation. Floating point representation is widely used in scientific computing, simulations, and graphics rendering. Many algorithms in machine learning and data analysis rely on floating point arithmetic for precision. Understanding floating point representation is crucial for optimizing performance in computational tasks. Conclusion and best practices. Floating point representation and IEEE 754 standards are fundamental to modern computing. Developers should be aware of limitations and potential pitfalls and floating point arithmetics. Adopting best practices such as using appropriate formats and managing precision can enhance computational reliability. Thanks for watching.